You're running a production line. Every step seems capable of keeping up with demand, and at first, everything flows smoothly. But as demand increases, small differences in processing time start to matter. One step slows the others down, work begins to back up, and the entire line starts moving at the pace of its slowest step. How do you identify the true bottleneck? What happens as demand gets closer to capacity? And why do constraints move when the process changes? There's a model for that. Welcome to Model Monday, a series where we break down scenarios in different industries, organizations, and departments and explain how you can build a simulation of them in Process Playground. Let's model it. This model is going to show a sequence of different simulations to replicate some of the issues that occur in theory of constraints. Theory of constraints is an idea that in any process, one step usually limits the performance of the whole system. If that step cannot keep up, work starts to back up before it, and the steps after it may sit idle waiting for work. We'll start with a base item called Item 1. Then we're going to create demand. We'll start with when our customer demand is not very heavy. So we're going to generate one item every 1.2 minutes, or every 72 seconds. As long as each process step can be done within that time, we shouldn't have any problems. We'll continue by adding the steps in our process. First, we're going to put all of those items into a queue. And then after that queue, we're going to create an activity called Step 1. Our processing time for this first step is going to be in seconds, and it will be a triangular distribution where we'll set the minimum to 48, the mode to 55, and the max to 62. There's potential that we might go slightly over 60 seconds, but not by too much and not very often. Then we're going to put in Step 2. We're going to put in a processing time with a triangular distribution of 48 seconds, 50 seconds, and 52 seconds. Then from step number 2, we're going to add step number 3, and we'll say it's a triangular distribution with a processing time minimum of 52, a mode of 57, and a maximum of 62. Again, those are going to be in seconds. For our last step, this will also be a triangular distribution, but it will be the most variable. It can be as fast as 39 seconds, with a mode of 49 seconds, and as slow as 59 seconds. Even though it has a 20-second range in processing time, it's still under 72 seconds. Finally, we'll include an exit block. Notice that there is no queue between any of the steps. In Process Playground, if an activity block has finished working on an item before the step in front of it has finished, the item will wait in the activity block. This is one of the ways bottlenecks show up in a connected line. If a downstream step cannot accept work, the upstream step may finish but still cannot release its item. In theory of constraints terms, that means that the bottleneck starts creating blocked time upstream. You can view how long items were waiting in this blocked state with the blocked time statistic we'll see later. Now that we've built this process, we can do some analysis on how long this process will take. If we add the modes together, we'll see that the overall time for the mode of this process is 211 seconds, which is about 3.52 minutes to get through the entire system from the time an item is created to the time it exits. This will be our nominal processing time. Now let's run a simulation. We'll set this to run for 100 minutes and we'll start it up. And we'll zoom in a little bit here. If we look at the total lead time through this process, we'll see that it's actually very close to our theoretical, 3.51 versus 3.52. When we have more capacity than demand, we can get as close as possible to the nominal processing time. Now let's take a look at the results from specific activity blocks. We can look at the blocked time, which shows how often an item couldn't move to the next step because the step in front was preventing it from doing so, as well as the idle time, which is how long the activity could have accepted an item, but there was no item available, and we'll apply that to all of our activity blocks. In our queue block, we'll take a look at the average length and we can see if anything was waiting before it could even get into the process. Finally, we'll include how many items were generated, which in this case was 84. Looking at the overall process, with more than 70 seconds between arrivals and very few of processing times taking over 60 seconds, we are able to keep up and the process runs smoothly with no blocked time. Our theoretical time of 3.52 is our baseline for when the line is lightly loaded. In theory of constraints, the interesting question is what happens when demand gets close to the limiting step and variability begins to matter. So what happens when demand increases? We'll reduce the time between arrivals from 1.2 to 1.1, or 66 seconds in between items. When we run the simulation, we're still able to keep up. We're actually producing more items, and our total lead time is still 3.51, meeting our nominal processing time. We do have a slight amount of blocked time, but for the most part, everything is moving through the process easily. Now we're going to change the demand again. Every minute, we're going to generate an item, 60 items in 60 minutes. The 60 seconds in between items is less than the max time we see in some of our steps. So let's run it again. We can now see that step 2 has a 2% blocked time. Step 2 runs faster than step 3, which is also the slowest step in our process. When step 2 is finished with its item, it can't pass it on if step 3 is still working, which leads to increased blocked time. Our total lead time has only bumped up slightly to 3.53, but let's see how this changes as demand increases even more. We will now try to generate 63 items in 60 minutes, or 0.95 minutes between items. That's an arrival every 57 seconds. The process starts to get more and more constrained. Our total lead time is starting to increase. We were previously at 3.52 minutes, and now we're around 4 minutes. We can see step number 2 is blocked about 10% of the time, and because it's blocked 10% of the time, step 1 starts getting blocked 4% of the time. Finally, we can look at the queue length graph here and see that although step 1 is starting to get backed up, the queue length is still stable. Let's increase our demand one more time. If we set the time between arrivals to 0.9 minutes or 54 seconds between arrivals, we can see how much our process begins to break down. Now our total lead time has gone up to 6. Our blocked time for step 2 is 10%, and the blocked time in step 1 is 3%. Now this queue is starting to get way backed up, with no limit to the growth in this queue. This is where theory of constraints becomes easier to see. When demand was comfortably below capacity, the line looked smooth. But as demand rises and gets closer to the slowest processing time, that limiting step starts to control the pace of the whole process. Upstream steps get blocked, time in system increases, and lead time starts rising even though none of the individual steps have changed. We'll reset the time to 0.95, which again is 57 seconds, and talk about how we can improve the process with the slightly increased demand. Let's run the model. We'll first look at step 2, which has a high blocked time of 8.15%. This tells us that step 2 is being held up by the step after it. This points us to step 3 as the current constraint, so we'll focus on our improvement there. You do process improvement, and your changes successfully reduce the time at this step to 45, 47, and 50. This 47 seconds as the mode is much less than the 57 in our demand. This also affects our nominal processing time, bringing it down from 211 seconds to 201 seconds, or 3.35 minutes. Let's rerun the simulation. Now, if we look across all of our activity blocks, step 3 now has the most blocked time, meaning that step 4 has become the limiting step. Our total lead time is close to our theoretical of 3.35 minutes, just above here at 3.38. But once again, let's increase demand. We'll set this to 0.9 or 54 seconds and rerun it. Notice how the lead time is getting a little longer, farther away from our nominal processing time. This is another key theory of constraints lesson. Once you improve the bottleneck often moves. The goal is not to fix the line once. The goal is to identify the current constraint, improve it, and then find the next one. Finally, let's say we had a problem at step 2, where suddenly this process step is taking 10 seconds longer across the minimum, the mode, and the maximum. If we rerun the simulation with this new processing time, you can see how step 1 now has a blocked time of 7.92%, making step 2 the new bottleneck. The bottleneck is not a fixed label on one step forever. It depends on the current demand, variability, and processing times. Change one step, and the constraint can shift somewhere else in the line. So in a nutshell, that's the theory of constraints model. But the real value is in what you can experiment with. By modeling a connected process with variability and increasing demand, you can see how bottlenecks emerge, how blocked time spreads upstream, and how the slowest step starts controlling the pace of the entire system. And it's not just production lines. The same pattern shows up in software development, hospital systems, warehouse operations, call centers, or any process where work flows through connected steps with limited capacity. From here, you can start to ask real design questions. What happens as demand approaches capacity? Which step is the current constraint? Should I improve the bottleneck, reduce variability, or add capacity somewhere else? And once I improve one step, where does the bottleneck move next? Those are the kinds of trade-offs this model is built to explore. That's the model. Now go experiment. Happy modeling!